All right, class. So what we started talking about, we said we're going to learn that if we have a flask and inside our flask we have a solution and we don't know what is inside this solution, we are going to use a spectroscopy to figure out what is the compound in here. And the two spectroscopy I'm going to go over, we're going to talk about IR and NMR to figure out what is in my flask. So far, so good. Okay. And this is a round bottom flask. I know it looks like a little bit like pumpkin. I know, but use your imagination. This is a round bottom flask. Now, before we talk about IR and NMR, do you remember from Chem 1A, the good old days, do you remember the electromagnetic spectrum that we had in Chem 1A? If you remember the electromagnetic spectrum or the EM spectrum, it had different types of light. It had different types of light because we said different types of light, they have different energy. If you remember, radio was the lowest energy. Radio is a type of light. It has the lowest energy. What's the one after that? Do you remember? Microwave, right? Microwave also pretty low energy. After the microwave was infrared, IR. Red. Hopefully I spelled it right. Then after that was visible. Okay. Then it was UV. Then it was X-ray. And then the last one was gamma ray. So gamma ray and X-ray, they have a high energy, right? Radio and microwave, they have low energy. This is why you should avoid getting exposed to gamma ray or X-ray or even UV, right? This is what they tell you to stay away from the sun because they have high energy. But radio and microwave, they have a lower energy. So when we go from left to right, the energy increases. Now, if you also remember in that chapter for Chem 1A, now energy is equal Hc over lambda. That's one of the equations we learned. And the other one that we learned was that energy is equal H times frequency. Okay. And speed of light is equals lambda over times frequency. Yeah, so these are the equations you did in Chem 1A. I don't want you to focus on that. I was just going a little crazy because I teach Chem 1A. So I wanted to remind you, do not forget my class. Now, what I want you to focus on is here. So this electromagnetic spectrum, we have different types of light. And different types of light, they have different energy. You can see radio is the lowest one, gamma ray is the highest energy, and infrared is the one we are going to focus on. Because what IR radiation does, it causes the excitation of vibration of covalent bonds. I'm going to talk about that in 1 second. So far, so good? Okay, so infrared IR is what we are interested in today. Now, let's talk about covalent bond for a second. What's the covalent bond again? Again, you have to kind of remember Chem 1A, two nonmetals together, right? Now, when you have a covalent bond, one thing I want you to kind of remember, that covalent bond is not rigid. Well, what does that mean? That means think of it like a spring. It is constantly vibrating in various modes. It's stretching and bending. It's very active. That's the way I look at it. That the covalent bond is very active. Is always stretching and bending and vibrating in various modes. Okay, so think about that. So covalent bond is not rigid; it's very active. It is it's constantly moving, stretching, and bending, and all that. All right. Now here's what happened when you shine light. When you add radiation to a covalent compound, what happens is the molecule is going to absorb the IR radiation. Okay? So I'm going to shine light and the molecule is going to absorb the IR radiation. And what happens is when it does that, when the molecule absorbs the IR radiation, the IR energy, the covalent bond starts vibrating. So the covalent bonds are going to start vibrating. When they start vibrating, now different bonds are going to be excited at different frequency. And that's really good for us because based on the frequency they get excited about, we can tell what type of bond we have. Okay, so hopefully you follow that. If not, that's okay. I'm going to go over it with you one more time. So what's going to happen? What's going to happen is we are going to shine light. Okay, we're going to shine light to a molecule. The molecule is going to absorb the IR radiation. The molecule is going to absorb the IR radiation, right? The IR is a different type of radiation, it's a different type of light. It's going to absorb that. When the molecule absorbs that, then what's going to happen? The covalent bond in that molecule, the covalent bond within that molecule is going to start vibrating. So, I'm going to shine light. The molecule is going to absorb the IR radiation, and the covalent bond in that molecule is going to start vibrating. So far, so good. Now, here's the key, that different bonds, they get excited at different frequency, right? And that's very key, that different bonds, different covalent bonds, they're going to get vibrationally excited at different frequency. Now, why is that key? That's key because then based on the frequency they get excited, we can tell what type of bond we have. We can tell what kind of bond we have. So far, so good? Okay. Now what we're going to do, we're going to use Hooke's law model to help us understand IR better. What we're going to do in the Hooke's model, we're going to compare a vibrating bond to a vibrating spring. Okay? So let's say I have an atom over here. I'm going to call it M2. I have an atom over here. Okay? And then here is my spring. Oh boy, I have to draw stuff. And then I have another atom over here. Now, what happens over here is that what's going to happen is the bond is going to vibrate back and forth. So the bond is vibrating. The covalent bond is going to vibrate back and forth. So this is what I mean by that. Think about the bond, the vibrating bond as a spring, right? It's going to be vibrating back and forth. It's going to be vibrating back and forth. All right, now for Hooke's law. Now here is the equation, right? Here is the equation. This is the frequency of molecule vibration. Basically, the rate it goes back and forth. So the frequency of the molecule that is vibrating, the rate of going back and forth, think about it like a spring, equals half times square root of K, which is a force constant. Basically, how easily does it go back and forth? Over reduced mass. Okay, so again, this K over here is force constant, and the force constant, the way to look at it is how easily something goes back and forth. Now, the reduced mass, this is a reduced mass, and the equation is basically M1 times M2 over M1 plus M2. Those are the two masses because we have the atoms over here. Yeah? Okay. Now, what do we get out of this is what matters the most. What do we get out of this? This is also called wave number. This is called wave number. And the unit is 1/centimeter. Okay? Now, as an organic chemist, and if you've taken my Chem 1A class, you know, I don't like math, right? So I'm going to put this in a language that I understand because I'm not a physicist. So here's a language that I understand. What this is a bond stiffness over masses. Okay, how stiff is the bond over the masses? This is something that I can understand that. So how stiff is the bond over the masses is going to give me a number. I'm going to call that a wave number. And the unit for that is 1/centimeter. So far, so good? Okay. Now, let's go over what we expect for the IR frequency. Okay. Now I need you to keep this in mind as I'm giving you different scenario. Scenario number 1. What happens if I have a heavier atom? So if I have a heavier atom, what does that mean? The mass is going to go up. If the mass goes up, what happened to my wave number? Again, wave number is the frequency of molecule vibrating. The rate goes back and forth. So if the mass goes up, what happened to the wave number? The wave number is going to go down, right? The mass goes up, the wave number is going to go down. Okay, so the heavier atom are going to have a lower wave number. So far, so good. Okay. Now, we can see that. And I'm going to show these numbers to you later. But carbon-carbon bond has a wave number of 1,000, 1/centimeter. Carbon attached to a Br has a wave number of 500, 1/centimeter. Okay, so here I have 2 covalent bonds. This one is heavier. The heavier atom, the wave number is going to go down. So the IR frequency is going to go down. You guys are good so far? Okay. Ready for the next scenario? Number 2. What happens if you have a stronger bond? What happens if you have a stronger bond? Now, if you have a stronger bond, so when we had a heavier atom, that means the mass was up. If I have a stronger bond, what does that mean? If I have a stronger bond, that means I have a higher K value, right? I have a higher K value. Okay, so I have a higher K value. If I have a stronger bond, which I have a higher K value, what happens to my wave number? This goes up, the wave number has to go up. This goes up, the wave number goes up. Okay, so if that's the case, the wave number is going to go up. Okay, now here's an example. Let's do carbon triple bond, carbon double bond, carbon single bond. Yeah, and carbon triple bond, this is an sp, right? sp2, sp3. So carbon triple bond, if I look at for the IR frequency, what it is 2200 wave number. Oh my god, I put MC instead of CM. Why did I do that? Okay. Carbon double bond is, do you expect it to be more or less? Do you expect it to be more or less? Remember, carbon triple bond, which one is stronger? Carbon triple bond or carbon double bond? Which one is stronger? Tell me. I can't hear you, but tell me anyway. Which one is stronger? The triple bond is stronger, right? So the double bond is weaker than the triple bond. So what do you expect? Do you expect this number to be higher than 2200 or lower? You expect it to be lower. So this is 1600 wave number. And carbon single bond is, you know that already, 1000 wave number. Okay. Now, this is really key. I need you to remember that. Because again, carbon-carbon triple bond is going to be the stronger one. Carbon-carbon single bond is the weakest bond. Stronger bond is going to have a higher wave number. Yeah? Okay. Ready for number 3? So we have the heavier atom, the stronger bond. Now, let's talk about polarity. The more polar a bond is, if you have a polar bond, if you have a bond that is very polar, what does that mean? If you have a bond that is polar, that means they have a different EN value. They have a large EN value, right? So if you have a bond that is polar, that means you have a large EN value. For example, if I have to give you an example, I would say OH is a polar bond, right? Oxygen is a lot more electronegative. So this is my polar bond because oxygen is going to pull electron toward itself. That's what it means by polar bond, right? So oxygen is has a higher EN value than hydrogen. So it's going to pull the electron toward itself. This is going to end up being a polar bond. Okay. Now, when you have a really polar bond, when there's a huge difference between EN value, because each one has an EN value. If the difference between the EN value is really large, you're going to be more polar, right? From Chem 1A. If the EN value has a large EN value between these two, you're going to have a polar bond because one guy is going to pull most of the electron toward itself. Now, when that's the case, when you have a large difference in EN value, so you have a polar bond, what do you think is going to happen? What do you think is going to happen? You are going to absorb more energy. You are going to absorb more energy. And because you are going to absorb more light, more energy, the peak size is going to be really, really large. So every time we have hydrogen bonding, every time we have H bonding, and H bonding, like I have OH, I have NH, the peak is going to be a very broad peak. What you end up having, you're going to have broad peaks. Again, it has to do that OH and NH, they are very polar. Those are very, very polar, right? Those are polar molecule. There's a large EN value. When you have a polar bond, it's going to absorb more light. If you absorb more light, the peak size is going to be really large. So when you have hydrogen bonding, your peak is going to be broad. And I need you to remember that because this is going to come back big time. So if you have an OH versus NH versus CH, for the OH, I'm going to have a broad peak. NH, a little bit less broad, but it's still broad because NH is less polar than OH. CH, not polar at all. My peak is not broad. So on the IR spectrum, this is the type of peak you see. OH, because OH is very polar, it has a hydrogen bonding, the peak is going to be broad. NH, also hydrogen bonding, but less polar than OH because oxygen is more electronegative than nitrogen. So then it's still broad, but a little bit less broad than OH. CH, not very polar. Carbon and hydrogen, their EN values are pretty much the same. They're very similar. So this peak is not broad. So this is what you are going to see on an IR spectrum. I haven't talked about IR spectrum yet. We will. These are the type of peak you are going to see. When you're polar, they end up to be a little bit more broad. When you're not polar, they end up to be a little bit more sharp. Yeah? Okay, beautiful. So far, heavier atom, you're going to have a low wave number. stronger bond, you're going to have a higher wave number. And we said the polar bond, again, the polar bond, what's going to happen because it absorbs so much energy, you're going to have a peak that is broader than a normal peak. Okay, one last one. Ready for number 4? Last one, you're almost there. Now, IR responds to changes in a dipole moment. Okay, again, what's a dipole? This is a dipole. They have different EN value. This one is pulling the electron this way. This is a dipole. Again, we're doing a lot of Chem 1 review today. So IR responds to the changes in a dipole moment, right? If polar covalent are very IR active, if you're polar and you're covalent, if you're a bond that is polar and covalent, what's going to happen? You are going to be very IR active. You're going to absorb that energy, and then you are going to be IR active. They get excited, and they can easily be observed in an IR spectrum. So you're going to show up on an IR spectrum. So far, so good. Okay, you're going to show up on an IR spectrum when you are polar covalent. Okay, look at this compound. Oh, this compound over here, this is covalent, this is polar. Bam, you are going to see it on an IR spectrum. Now, let me give you another example. How about this covalent compound? No, this is not polar. Right? This is not polar. And what does that mean? This is not going to be IR active. You're not going to be a CI. This is not going to be IR active, because to be IR active, what you want polar and covalent. Those are very, very much IR active. Now, if I have a compound like this, not going to be really IR active because this is a non-polar compound. So far, so good? Okay. All right. Now, what I wanted to give you an idea of where the peaks are going to come from. Okay. Now, to kind of summarize what we talked about. So we're going to talk about IR. We're going to talk about IR. If I have a solution, I don't know what it is, I can figure out based on IR and NMR. Today is IR. And then IR, we talked about the EM spectrum, the infrared, the IR. This is what we are interested in. When you have a covalent bond, is not rigid, it's like a spring. It goes like back and forth. You shine light, it absorbs the IR radiation, and it starts vibrating. It's going to start vibrating. Now, when this is vibrating, the nice thing about it is that different types of covalent bond are going to vibrate at different frequencies. So depending on the frequency you get a vibration, you can know what type of bond you have. And I like this more. This is a wave number, bond stiffness over masses. So that means if I have a higher mass, I have a lower wave number. If I have a stronger bond, I have a higher wave number. And then if you have compounds that are very polar, like OH, like NH, what you end up getting broad peaks. And remember, to be IR active, you need to be polar covalent. Alright, so this was all to kind of give you an idea before I put the spectrum on there. Here's what I wanted you to know. We're going to talk about IR spectrum. IR spectrum, of course, is going to have a x-axis and y-axis. Now, you know what? I don't want to put the arrows here. Hopefully you didn't put it either. On this side, we are going to have absorption. And here, we're going to have wave number. You know what that is? 1/centimeter. Okay. Now, IR spectrum is a little bit interesting. Because when you come down here, okay, the numbers are going to increase. And when you go right to left, the numbers are going to increase. Okay. Now, let's go over this together one more time. So the bonds in a molecule Each one is going to absorb the IR radiation at a particular frequency and get vibrationally excited. So when you have a molecule, the covalent bond in that molecule, each covalent bond is going to absorb the IR radiation at a particular frequency and get vibrationally excited. So far so good. Okay. So the most useful information from IR that you can get is what functional groups are present. Different bonds get vibrationally excited at different frequency, so we can tell what type of bond we have. Now, let's go over this one more time. What is the most useful information you can get from IR? Functional group. Oh my goodness, I can't spell. It's so hard to spell in this. Alright, functional groups are the most useful information you can get out from IR. Different bond get vibrationally excited at different frequency, so we can look at this frequency and figure out what type of bond we have. Alright, you feeling pretty good? You ready for me to put out an IR spectrum? Let's do it. Okay, so you have this package, okay? Don't freak out. You have a package, take it out. And first, I want us to do nothing, just look at it. Let's go to the next page. I just want you to look at this. Don't do anything. Look at this. Kind of cool. You have no idea what it is, but it's okay. It's the IR spectrum. Just want you to look at it. So like if you see this, you go, oh, I know what that is. That's the IR spectrum, right? Okay. So as you're looking at this spectrum, these are IR spectrum. One thing I want you to pay attention to is that here, again, as you come down here, it is increasing the intensity of the IR absorption. And then here are my wave number. And you see how these are the peaks, right? They have a lower peak, higher peak. This is why as you're coming down, the intensity gets increasing. The intensity is increasing. And these are wave number, okay? All right. Again, these are IR spectrum. I just want you to look at them. Take a minute. Look at these IR spectrum. See what they look like. All right. Now, remember what we said. I want to say this one more time. I want to say this 10 more times until you're good with this. Most useful information for IR are the functional groups. What functional groups are present is what helps the most. Now, here's how I would like to look at the IR. When I look at the IR, there are a few things that I look at, okay? I'm actually going to move this over. Perfect. Here's how I look at IR. Whenever I get an IR spectrum, here's what I say to myself. There are a few regions I'm going to look at. At the very end, this region over here, I'm going to look at for OH and NH. Because if you remember, we said when you have hydrogen bonding, right? When you have all those very polar bonding, right? You're going to have these broad peaks. So I'm going to look at NH and OH that happen around this region. Then the next region, what I'm going to look for, I'm going to look for CH. They're not very interesting. Most things have CH. But that's okay. Then what I'm going to look for, I'm going to look for triple bond. Those are pretty unique. Okay. Then the next region, what am I going to look for? I'm going to look for carbonyl. Those are very useful. Okay. Now, anything after that, not very useful. We call them the fingerprint. We call them the fingerprint. Not very useful. I mean, you can still get some information out of it. But what I mainly want to get out of IR are the functional groups. And I can do that looking at these regions. So far, so good. Okay. Now, I'm also going to add, let's see. All right. I'm also going to add C double bonded to N. I can figure out a triple bond over there. Okay. Now, let's look over here. Let's look over here that I mentioned. Now, over here, These are the OH and NH. And if you remember, we said they are going to have a broad peak. So what I'm expecting here, I'm expecting a broad peak over here. This is the region right here. I'm expecting the broad peak around over here. Now, that is the zone 1. You can see here 3700 to 3200. Again, you have the alcohol there. You have the amine and amide there. There is a stretching for alkyne there too. Now, the next zone, 3200 to 2700. CHs, they're not very useful, right? Because pretty much everything has CH. So this region I'm more excited about. If I see a broad peak, I go, oh, I have OH, I have NH. Okay, now again, zone 3, you can look for triple bond. That's just very helpful. Zone 4, that's very helpful. I can look for different types of carbonyl, right? And aldehyde, ketone, and that's very useful. Okay, and then zone 5, also useful. Again, you have this table in front of you as you take an exam and doing practice problem. But NMR will be better for this. We'll talk about it in a second. Now, my plan for today is for you to get used to looking at an IR and decide what type of functional group you have based on IR. To me, the most useful thing I can get from IR is this one. What type of functional group I have? What type of carbonyl do I have in this zone? So far, so good? Okay. Now what we're going to do, one by one together, we're going to look at this IR spectrum. You ready? Okay, have this in front of you and have this in front of you. All right, here, what do I see? I see something here. This is kind of interesting. What's going on here? Oh, I have it here too. Oh, I have it here too. What is in that region? CH. Is it useful? Not really. Most compounds have CH, right? Okay. Not particularly useful. But when I look at the one on the top, ooh, this stands out to me. Yeah, around 2000-ish. I have that, a sharp one. What is that? That is a triple bond, right? That is a triple bond. So that's useful. I can see that I have a triple bond over there. So look for that region. I don't have anything in this region, so I don't have a triple bond here. Okay. Now, let's look over here. Whoa. This is far left and is broad. What is that? That is going to be my OH. We talked about that OH has a broad peak. It could also be NH. NH is not as broad. Again, we'll get to him to see what NH would look like. So, again, far left, I'm looking for OH and NH. CH, they all have CH. And then triple bond is very obvious. And then the carbonyl, because you saw the triple bond was very, very obvious. So far, so good. Okay. I have no C double bond O here. So I know I don't have any sort of carbonyl going on here. Let's go to next page. Pause me. Try to look at this yourself for a second. If I look over here, I'm going to say, okay, I have this. I have CH. Big surprise. Now, you can also look at what you don't have. I said, oh, I have no OH and I have no NH. That's a good piece of information you have. Oh, I have no triple bond here because there's nothing there. Good piece of information. Oh, what is this? That is a carbonyl. That is a carbonyl. So I know I have some sort of carbonyl. So again, it's kind of, IR kind of lack of having it is just as good as having it because you know what you don't have. So you always go, this region, do I have NH or OH? This region, do I have a triple bond or no? This region, do I have a carbonyl or no? Okay, and then you can go eliminate later what type of functional carbonyl do we have. So far, so good? Okay. All right, now let's look at this one. This one, I don't have any OH. You agree? No OH, no NH. That is also helpful. No triple bond. Okay. Ooh, I have this. What is this? This is a carbonyl, right? Okay, I have a carbonyl. Now, let's go over this carbonyl for a second. What you have here, you see you have a peak right here next to that CH peak. It's a medium-sized peak next to CH. That is for the aldehyde. That is for the aldehyde. That's how you would know when you have an aldehyde. You have a medium-sized peak next to the CH peak. Okay? And that's that's very helpful. And when you have that peak next to the CH peak, you know you have an aldehyde. And this is my aldehyde peak. So I have a carbonyl peak, I have an aldehyde peak, then I know I have an aldehyde. So far so good? Okay. Again, what I want you to get out of this is not so much what your entire compound is. It's kind of like, can I figure out what type of functional groups I have? Can I figure out what I don't have? Because that's also as useful as, as not as having it. So over here, I have another carbonyl. So I know I have a carbonyl. Now, I can eliminate some of them. I know it's not an aldehyde because I don't have that. I know it's not an amide because I don't have that. I know it's not a carboxylic acid because I don't have an OH. So you can eliminate. So you can eliminate one by one. You're feeling good so far? Okay. Now, based on everything we've talked about, let's do this one together. You are going to look at this and you're going to tell me, look at this IR. I can tell you what I don't have. I have no OH or NH. Okay. I have CH. Okay, that's cool. That's not very useful. We always have CH. Okay, this is good. I have no triple bond. I can tell you that because there's nothing there. And, I have a carbonyl. I have a carbonyl. So that is useful. But now, what kind of carbonyl do I have? You can eliminate some of them. Do you have a carboxylic acid? No, because you don't have an OH peak. Do you have an amide? No, because you don't have an NH peak. Do you have an aldehyde? No, you don't have a medium-sized aldehyde peak next to the CH. Okay, that's not bad. Now I'm just stuck with ester and with ketone. So that's really helpful to go one by one what I don't have. All right, let's look over here. Now, I look over here. The first thing I go, I have some sort of carbonyl. Now, do you see over here, you have this CH group, but it's kind of broad. It looks like it was going to be an OH, but it's not as nice and as round as OH. Okay, so whenever you have this is a signature for carboxylic acid OH. The carboxylic acid OH, I call it an ugly OH because when you have an OH that is an alcohol, see how nice and broad this peak is? Now, when you have a carboxylic acid, that becomes a little bit ugly. So the broad, ugly OH usually means carboxylic acid. So I had the carbonyl peak, which was great. Now I have the ugly OH, so I know I have a carboxylic acid. So far, so good? Okay. Again, there is a lot more information you can get out of IR. And then this list is going to help you out. Have this in front of you. It tells you all the little thing, what to look for. But when I do IR, the first thing I go, okay, OH and NH, do I have it or not have it? That helps. CH, everything has CH. Triple bond, do I have a triple bond? And then carbonyl, do I have a carbonyl? And then you remember that if you do have a carbonyl, then you have to eliminate. Do I have an aldehyde? Do I have a ketone? Do I have an ester? Do I have an amide? Do I have a carboxylic acid? You can eliminate some of them based on the IR. You can eliminate carboxylic acid because you have to have an ugly OH, right? You can eliminate amide if you don't have a peak over here. You can eliminate aldehyde if you don't have a peak next to the CH group. So elimination is just as important as figuring out what you have for sure. So far, so good? Okay, I'm going to stop right here. But before I stop right here, So we did well today. We went over the IR. You look at the IR spectrum. You go, okay, this is the IR spectrum. I know what it looks like. What am I looking for? I'm looking for functional groups, right? Get the functional groups out. There are 4 regions that I'm going to focus on. Do I have OH or NH? CH, do I have a triple bond? Do I have a carbonyl? And if I do have a carbonyl, let's see if I can eliminate which one I can eliminate that I don't have to figure out what I have. It's like over here, we did this problem. You go, oh, carbonyl. I have an ugly OH. Is going to be a carboxylic acid. I have a carbonyl. I don't have an OH. I don't have an NH. So it's not amide or carboxylic acid. I don't have an aldehyde peak. It's not going to be an aldehyde. So it's going to be ketone or ester. Then we're going to learn later on to keep going further and further. All right. Beautiful job today. This is the IR, and we're going to talk about NMR next time. And we're going to do a lot of IR and NMR practice problem. You will have this on the exam and when you do practice problem. So have this in front of you all the time. Have this page in front of you as you're doing the practice problems. All right, really nice job. Thanks for hanging in there with me. I will talk to you guys next time.